So now we're going to go on to the concept of titration. So titration, we can also call volumetric analysis. And so you will do quite a lot of practicals on these in class, I would believe, because it's really good to do these hands-on to help you get a really good understanding of how these actually work. So in volumetric analysis, we first of all need to be able to distinguish between the terms of endpoint and equivalence point, because these are two main factors which we need to compare and contrast in order to make an understanding of the pH of these points in our titration so that we can get accurate results. We also want to be able to recognize that acid-base titrations rely on the identification of an equivalence point. And so this is by measuring the associated change in pH using chemical indicators or pH meters to reveal an observable endpoint. We next need to be able to sketch the general shapes of graphs of pH against volume. And so this is what we call a titration curve. And so we need to be able to do this involving both strong and weak acids and bases and various different combinations of these. We also need to be able to identify and explain the important features of these titration curves. And so this is going to include both the intercept with the pH axis, the equivalence point, the buffer region, because we are bringing in all these concepts which we've already discussed, so buffers as well, and the points where pKa equals pH or pKb equals pOH. So we can see that all our concepts which we've been learning throughout acids and bases and equilibrium all sort of ties together when we bring it all together in the concepts of titration. We also want to be able to use appropriate mathematical representations and analyze experimental data and titration curves to solve problems and make predictions, including using the mole concept to calculate moles, mass, volume, and concentration from volumetric analysis data. I think it's also really important to note that you will be required to create a titration curve and understand and draw information from these titration curves based on data that you have been given. And then finally, we've got a point here about a mandatory practical. So in class, you'll do acid-base titrations in order to calculate the concentration of a solution in reference to a standard solution. And so that's a really important practical because you are fully assessed on the concepts which surround that practical, because it basically ties completely into everything that you learn in relation to titration, and it's very helpful. So it's really important that you pay attention to that. So when we consider endpoint versus equivalence point, we want to talk about what equivalence point is. So equivalence point is a quantitative measure, and so it's going to be the point at where the acid and base concentration is equal to the conjugate acid or base concentration. So for example, if we have an acid like HCl and it dissociates into H plus and Cl minus, the point at which H plus is equal to HCl is going to be the point at which the equivalence point has been reached. And the end point is then going to be a qualitative measure. And so by qualitative measure, this is meant where the change in color occurs. And so this ties back into when we were talking about indicators, because the indicators are used with the buffering in order to determine where the endpoint is. And so the endpoint provides us with an understanding of where the equivalence point is. So it's an approximation for where the equivalence point is. And so the endpoint is our qualitative measure, which is the actual point where the color change occurs. And so you have to note that you need to stir the solution. Like if you've stirred the solution and the color appears, the endpoint has not been reached. So the endpoint actually needs to be reached via just the means of the reaction progression, as opposed to any particular manipulations of the reaction. And so if you think about it, at the equivalence point, there isn't a difference in color because they're at equal concentrations. But after this point, one of those concentrations, so in the example of HCl and H+, so where HCl is the acid, H+ is the conjugate base, one of those is going to become dominant, so that being the H+, and so this is what then causes the change in color. And so that gives us, at that exact point when it changes color, is going to be slightly after the equivalence point, but we say that that is giving us a representation of the equivalence point because it's as close as possible to the equivalence point that we can measure visibly. And so there can only be one endpoint, and that's going to be at a particular pH and color, but there can actually be several equivalence points, and so that's going to be all those points at which the acid or base is equal to its conjugate acid or base. And so that may not necessarily be observable because we might not see that change in color until there's actually one particular concentration that is then seen to be more dominant than the other. So this is what a typical titration graph will look like. So with this one here, if we're looking at the red line, we're considering a titration of a strong acid. So, and we're considering what happens with a strong acid if we were to add sodium hydroxide. And so you may not remember, but we said before that sodium hydroxide is what we consider to be a strong base. So if we're to add a strong base to a strong acid, such as HCl, we can see that we're starting off with a very low pH because we've got HCl only in our reaction vessel. But then once we start adding our mils of 0.1 molar sodium hydroxide, we can see that we have a bit of a buffer region where the pH is somewhat being counteracted, but then we have this sudden change in pH. And so we determine that our equivalence point is at pH of 7. And so this is because if we have a strong acid and a strong base, it's going to be entirely neutral at a neutral pH. Whereas if we have something, for example, like a weak acid with our strong base, we can see that we're starting at a higher pH because it's less acidic. We have, with the addition of the strong base, we have this bit more pronounced increase in pH due to it being a much stronger base in comparison to the strength of the acid. However, we then see the buffer region at around pH of 5, where we're trying to counteract that change in pH of adding the sodium hydroxide. But eventually there's been so much sodium hydroxide added that the system can no longer be buffered. And so we then have the weak acid, so the acetic acid, being entirely neutralized by the sodium hydroxide, resulting in a pH equivalence point that is above 7, so at 8.72. And so that's because a strong base like NaOH is going to have a greater pH naturally than a weak acid in terms of its extent of how strong it is. So the strength of the base is stronger than the strength of the acid. So it's going to be greater directed towards a high pH or a more alkali pH than the acidic pHs, because there's more hydroxide ions in solution than there will be of hydrogen ions in solution. And that's because the extent of dissociation will be greater for the sodium hydroxide than the extent of dissociation for the acetic acid. And so that's different than titrating with the strong acid like HCl, where our equivalence point is at 7, because when we've got our equivalence point of around 7, we're saying that the extent of dissociation of hydrochloric acid is going to be very similar to the extent of dissociation of the sodium hydroxide. So the point at which they are neutralized, or which they neutralize each other, is going to be at a neutral pH, because the hydroxide ion concentration will be roughly equal to the hydrogen ion concentration. And so we also can notice that along the side here we have some ranges. And so we've got a methyl orange pH range, a litmus pH range, and a phenolphthalein pH range. And so phenolphthalein is typically used for a weak acid, strong base type titration, and that's because it favors higher pHs, so pHs greater than 7, so in that range of 8.5 to 10. Then we can see a litmus pH range. So litmus might be used for a strong acid, strong base reaction, and that's because it has a pH range which is fairly neutral, so from around 4.5 to 8, so you can capture that equivalence point of pH 7. And then finally we've got methyl orange, which has its pH range at 3 to around 4.5, and so that's because that's one which we would use in the case of potentially a strong acid, weak base titration. And so that's because a strong acid, weak base titration, we would expect that there would be an equivalence point within a less than 7 region.